Okay, what we're going to do today is finish this last primary topic called filtering sampled continuous time signals. I've handed out a worksheet that goes along with this. This is the basis of some of the material that's on the homework that's going to be turned in next Monday. This is also the basis for things that are going on as we transition into that lab number 9 with the touchtone decoding. So this is where we left off. Actually, we were right on this slide, and this is where I hung out in an infinite loop trying to get the video to process, because this is where it freaked out. It was right when I got to this slide from last time. This was the moving average filter, which you did in the first part of lab number 8. I don't think anybody had a question at the end, but does anybody have a question now about the math? Remember, we were going through this model right here and using the finite geometric series to finally get things worked down into this form here and here. So there's basically two pieces that go along with the moving average filters. There's the amplitude part, which is controlled by that ratio of signs and parentheses, and then there's the phase part, which is that linear phase, as it's called, linear because it linearly slopes down at L minus 1 over 2 is the slope. And at the very end of this chapter, I'll make a comment about the significance of that, but it's something that you've also observed in the lab. They had you observe in that very first part, namely the delay that gets imposed by the moving average filter. But this other really important topic in applying digital signal processing to analog signal processing is this topic right here. So we've been focusing in this chapter on just the filter part. But now suppose you want to build a DSP system, and that's what you're going to be heading into in lab number 9. Those are the types of things that I talk about in the real-time DSP class and in the 1-credit DSP lab that's offered in the fall. How do you actually go beyond this and say, now we want to wrap this filter with an analog to digital converter so we can process analog inputs and more than likely put a digital to analog converter on the output so we can send the filtered signals back out of the system again. And this scenario is played out in a lot of different contexts. We've seen this in the class before when we were doing sampling theory, but now we actually are modeling something that's useful stuck in between. Namely, we have a filter stuck in the middle. So we might choose to bring in an analog signal, process it in a particular way with a filter, and then ship it back out again. Or we might just simply bring the signal in and filter it and prepare it for maybe doing some digital demodulation on it to get the data taken out of it, in which case then we just use this much of the system. We'd have a capture system and then just stay in the digital domain. Or we might have a production system where we just use that half of it. You could visualize where you have a bunch of digital data stored representing, what's a good example of something that most of you probably have and some of you have been doing throughout the day so far?
Music files?
Yeah, listening to music on a music player of some sort, whether it be an iPod or some other device. That's taking digital data that's probably in a compressed format, decompressing it so it's running a bunch of signal processing algorithms, which could be filters in combination with other decompression algorithms, and then outputting it to a digital to analog converter. You do it all the time and you don't even think about it, but it is an electrical engineer's job to do that. Computer engineers are involved with that as well. Or in the case of your cell phone, it happens like this too, except it happens in a more sort of distinctive way in that On the cell phone, the continuous to discrete processing happens when you're talking to somebody, and then the sequence right here would go through a speech encoder that speech encoder would compress the speech so that it would take less bits per second to transmit it. Nominally, you could say speech sampled at 8 kilosamples per second, and nominally 8 bits per sample would be 64 kilobits per second to send that speech waveform as in a digital medium. So the airwave, it's encoded and sent through some analog modulation scheme, but actually what we do with the speech encoder is compress it in real time using what's called a speech vocoder. Vocoder means coder and decoder together, but it's a pair of circuits or pair of systems. So the encoder is at the transmit side and the decoder is at the receive side. So the speech gets compressed down to around 10 kilobits per second, and then it gets sent out as digital data. That digital data gets impressed upon an analog-based carrier signal in a microwave frequency band. Say it's either at 900 megahertz or around 1800 megahertz if it's the PCS band for cellular telephony. And then that analog signal gets reprocessed through a radio receiver, and eventually out comes a series of bits which represent the encoded speech. And then the encoded speech gets reformatted and decoded into speech samples. And in the process of doing that, then effectively this is where the information would come in through that processing chain. There's probably some more digital filtering, and then finally out through the earpiece as you hear it. Make sense? Is it inspiring to know that, again, electrical engineers are responsible for all of this, and signal processing is interior to all of that? And if you think digits is the only thing we deal with, that's not true. I mean, there's the communications modulation and demodulation is a microwave RF signal that has to have decoded off of it the ones and zeros. So there's many stages of processing, but digital signal processing factors in various different places, not even just the speech signal itself. It's actually involved with modulation and demodulation of the signal onto the microwave carrier. It's just done at a higher speed and at a wider bandwidth. It's not something that you would do in as simple electronics as, say, the audio would get processed. So this block diagram, although it seems so generic, it's got applications to a lot of things. So the way we're going to use it, though, is we're going to look at it as an end-to-end system onto itself. And this is also a good sales pitch for digital signal processing, although it doesn't always apply. It says if you can instantiate the hardware, namely the analog to digital and digital to analog, and then have the DSP microprocessor, FPGA, custom ASIC, whatever, sitting in the middle here to allow you to flow samples in and out through some difference equation algorithm, then you can tell somebody, I can build almost any kind of filter that you could imagine, and I can make it flexible. It can be in software. I can reconfigure it on the fly. I can do all these great things with it. Just let me tell you about it, basically. And of course, that's been going on for quite a number of years now, but it's not as old as a lot of other EE technologies would be. Really, DSP got a major kick start or kickoff in about the mid-60s. And that was mostly driven by military and government stuff where mini computers and mainframes were doing DSP back then. You can't even imagine a mini computer, right? Because you don't even know what I'm talking about when I say a mini computer. A mini computer was the first type of computer that was less than a huge room full of stuff that I can remember. I mean, when I went to school, it was a mainframe system that we programmed on, and we used punch cards, which seems really cryptic now, but we had to type everything out on paper punch cards and then go to a card reader, and our job would get loaded and our program would then run, and then we'd get a printout. Never on a terminal. It was always just a printout, and you would pick it up. There would be a header that would come out on it that would have your name on it, and that's how the operator would know where to put your printout. It would go alphabetical. So for me, I'd go to the W's, and that's where I'd get my printout. And you'd hang out there waiting for your printout, wanting to know, did my job run? Did it have an error? And if one page is all that showed up on your printout, that was generally a bad sign. As I'm now thinking of it, that meant that your job failed somehow or another, but you didn't know maybe for an hour or so. So it was kind of like the students that did that were like, if you're a student working in the library, I'm getting sidetracked now, but it's kind of interesting how it's changed so much. The big printers would just print job after job after job, and a job kind of like a student librarian position would be today would be to take those stacks and stacks of printouts and just go through them looking for the headers and separating them by headers, thin stacks, thick stacks, and then go through and pop them into the alphabetical slots for people to come by and pick them up. Nobody does that anymore at all. So the mini computer, though, was something that fit in a rack that could stand in the corner, maybe as tall as the electrical box is over there on the wall. And that was something that a DSP person could start working with. That was before my time, too, that stuff was happening. But then, it quickly started to change into the 70s and the 80s. And, it's just continued to grow and grow and grow since then. So a class that discussed this material would not have existed except as a graduate course. When I was in school, I didn't take any courses like this because they didn't exist. They were for graduate students, and I wasn't interested in this, or I didn't really know enough about it to be interested in it, as it turns out. So this is what makes DSP interesting, is being able to process analog real-world signals. And how do we make those connections? We're now in the position that we can pretty much do all of that, at least in a mathematical framework. To see it all connect together in a hardware framework, you'd have to take another class to do that. So if we have an analog signal that's coming in as a complex sinusoid, and honestly, I kind of wish the book would have taken a different approach, but I'm going to take a different approach in my example. It's a complex sinusoid here, but in reality, the A to D is not going to be a complex sampling A to D. It's just going to take a real signal. So it could also just be, X magnitude cosine omega t plus the angle of X, assuming X is a complex constant. So it could be a real cosine. They just chose the complex sinusoid because the math notation is a lot easier. So we sample that signal with sample spacing t sub s, and then it becomes a sequence. So this omega times t sub s, remember, that became our digital frequency variable omega hat. So now we have a signal into the discrete time domain, and it's a sequence, and that's the x of n that we have right up in here driving into our digital filter. And of course, when we do this sampling operation, we've learned already that what do we want to make sure we obey to avoid misunderstandings later? We have to sample according to the low-pass sampling theorem, which says we have to make sure that our sampling rate is at least greater than twice times that maximum input frequency. Otherwise, we have aliasing. But assuming we don't have aliasing for the moment, that sequence that comes out, this guy right here, is now in the discrete time domain. And stopping along the way, this is the summary of the important equations we need to work these problems. this relationship here takes us from the analog to digital, and then when we get done and we want to go from analog or digital back to analog, we have to use this last equation. So these are key equations. We start off with F, and we want to get omega hat. Later on, when we're coming out of the system, we have omega hat, and we want to get F back again. So what this relationship is saying, though, that the sequence goes in as a complex sinusoid, and then it picks up the magnitude and phase shift applied by the filter at that frequency, and we know then that that's the output Y of N. So now if we want to then take the last step, and that is go back to the continuous time domain, we just have this equation that we just started with, but now we're going to rewrite it and say omega is equal to omega hat over Ts, or the way I had it written on the previous page, I had it as F in hertz is equal to omega hat over 2 pi times Fs, because Fs is 1 over Ts. So now we're in the position that we can just map through to the output and have this relationship right here. We have the frequency response now on the digital frequency axis gets remapped by replacing omega hat by the 2 pi F over Fs. And then the analog frequency comes back out as the original analog frequency, which would be 2 pi F over Fs in terms of this notation from the omega hat value. This is more along the lines of what the book does. My preference is to get right down to the physical and work with everything in terms of hertz, because that's the way you work with the lab equipment when you're doing measurements. So there's no really complicated math here, except for the hardest part about the math right now is having to evaluate that guy at a given frequency omega, or equivalently in terms of omega hat, it would be that. And that requires some complex number manipulation. So as an example, here in the notes, and then we'll work on a second example in that worksheet I've handed out. Suppose we have a 5-point moving average filter that's wrapped between a C to D, which is our continuous to discrete, and our D to C, which is the discrete to continuous, or digital to analog, sampling at 1,000 hertz. The input has got 2 sinusoids in it, a cosine at 100 hertz and a cosine at 300 hertz. And the first cosine has an amplitude of 1, and the second one has an amplitude of 3. So the first thing we should ask ourselves is, are we going to have any aliasing issues? No. Why not? We're sampling at 1,000 hertz. Okay, so comment was made, doubling 300 is still less than the sampling frequency. That's correct. Or spinning it around another way, 300 is less than 1,000 over 2, or the folding frequency. Either way you want to look at it. So we're safe. I'm going to talk about later in the example what would happen if we alias. And I'll just maybe make a little comment right now. If the folding frequency is 500, suppose this was 700, right? What does that alias to? 300. So the way the whole math would work on this is, as soon as the signal gets sampled and violates sampling theory in this block diagram, which is way up over here, As far as the rest of the system processing goes, if the 700 folds aliases to 300 effectively, it's going to go through that filter as if it were originally at the 300, because the digital filter knows nothing else except, the principal alias value. And then when it comes out of the system, it picks up the gain in the phase of the filter at that frequency, and then it comes out of the system at 300 hertz, right? Because again, it can't do anything else. I always think of the aliasing business as happening right up front. As soon as you sample and you violate the sampling theorem, that's when the crime is done, and it's all over with at that point. You're never going to recover from it without a priori information, of course. So I also said plot the frequency response, so I just used MATLAB and FreakZ, and I plotted out the magnitude and phase in terms of the omega hat axes, running from minus to plus pi. But then because of an equation that I presented right up in here, that tells me that I can take that digital frequency response that I had in terms of the omega hat axes, and if I just remap omega hat to be 2 pi times f over fs, I could just replot that frequency response and then have it in terms of the underlying analog frequency axis. In other words, how the system behaves with regards to the analog signal that's passing through. So, let's see. That's what I did right here. I just simply replotted. I replaced, for my frequency axis on the plot function, I replaced it with the omega hat, which was W in the MATLAB notation, times 1,000 over 2 pi for both the magnitude and phase. So now I've got the exact same plot in terms of the vertical axes, but the horizontal axis has just been rescaled. So this is now F, which was omega hat over 2 pi times Fs. See how easy that is? As a matter of fact, at times I think I probably already said that you can always just lay another axis down here. That would correspond to pi, minus pi, and 0 if we were talking about the omega hat axes. But doing it like this is kind of nice because now we can see exactly where the 100 hertz signal is going to hit the magnitude and phase response of the filter, and where the 300 hertz sinusoid is going to hit the magnitude and phase response of the filter. So if we could pluck out those functional values, we'd know exactly what the filter is going to apply to the sinusoids that come in. Remember, one sinusoid has an amplitude of 1 and the other has an amplitude of 3. So those sinusoids at those two frequencies, 100 and 300 hertz, are now going to pick up some additional gain scaling and phase shifting from the impact of the filter. And you were playing around with that last week in the lab, remember, but you were doing it all in the discrete time domain. Now we've applied these two blocks to the outside, so now we want to see how it behaves from the outside terminals. In other words, the analog input and the analog output. So one approach to doing that, and you can take the analysis different ways, but I'm going to be more conservative. I'm going to say let's just take and convert to the omega hat variables. So on this side we have F in hertz, and this side I have the omega hat in radians per sample. Just go through the conversion in the forward direction, which is obtained by taking 2 pi times the frequency over Fs. So that gets me 0.2 pi and 0.6 pi. So I now need to go in and find out exactly what the magnitude and phases are at those two values, 0.2 pi and 0.6 pi. So this is the frequency response of my digital filter, magnitude and phase. Plug in the 0.2 pi to find out what the gain and phase is at 100 hertz. So this is relative to the 100 hertz. This is what happens to the 100 hertz signal. And this is what happens to the 300 hertz signal. Is everybody following this? It's just finding out what impact the filter is going to have on that signal. Question?
And we got L from the fact that it's a 5.2 in the average filter.
Exactly, yeah. L was set equal to 5. We already have an idea about what the filter is going to do because I went ahead and made this picture, and those red dots indicate what the gain and the phases are just pictorially. We don't know the exact precise number. We can guesstimate it just by looking at the picture, but what we get from down here are this is the exact amplitude, and that's the exact phase shift. This is the exact amplitude, and that's the exact phase shift. They make sense though, right? One was greater than a half, the other was less than 1/2. They were both negative values. I mean, the phases were both negative values. Those are both less than 0. And this one up here is like the 1/4, and that's the 0.6 something or another. So now all we have to do is apply those to the input sinusoid. So in the case of the 100 hertz sinusoid, it had an amplitude of 1. So we come down into this first expression and we get 1 times the 0.6472, and that's what's sitting out in front. And then we have a phase shift that just simply gets dropped inside the argument of the cosine. Remember how that works? That was last week's quiz, actually. And then for the second sinusoid, it gets this magnitude and phase applied. So we have here, we have to put in the amplitude of that cosine wave was 3 times the 0.2472. So that's how we get the 0.7416. And then that minus j 0.2 pi gets dropped inside of there. And I worked this problem differently at first, so I had the minus 1.2 pi and then I had a plus pi, but that nets out to being the same as minus 0.2 pi. Reasonable? Is it all that complicated? Question?
How do you find F?
Okay. Okay, that's a good question. It's a back-of-the-envelope type equation, fortunately. Oops. That's why I put all these equations in the box up here. So initially, when you want to get F, well, initially, when you enter from the analog to digital, you need to find the omega hat. So that's that equation right there. And then to get F at the end, you go from your omega hat back out through this bottom equation.
So when you're solving for omega hat, what do you plug in for F?
I plug in the frequencies of the cosine waves. In this particular problem, we had 2 cosines going in. One was at 100 hertz, right? The other was at 300 hertz. And even if we aliased, even if we put in 700 hertz, the first step of the problem would be look at the frequencies of the sinusoids going in, and then look at it again with respect to the sampling rate. So if it was 100 and 300, we know that those are principal aliases, right? So we don't need to make any adjustments. If it was, say, 100 and 700, then we would have to say 100 stays as 100, 700 with respect to a 1,000 hertz sampling rate folds down to 300 hertz because of the principal alias is 300. And then we do our analysis with the omega hats in terms of the principal alias frequencies. So crank out those two omega hat values, 100 over 1,000 times 2 pi and 300 over 1,000 times 2 pi. And then evaluate the digital filter's frequency response using those omega hat values. And then apply those to those cosine waves at those frequencies. And then we're basically done. Actually, the bottom equation, this one down here, doesn't really get used unless you've lost track of what you've been doing, because you knew that which omega hat value corresponded to 100 and which one corresponded to 300 from the very beginning. We'll go look at the worksheet right now, but I'm going to take a look at this last page just so we'll have this stuff wrapped up, and we'll move on to the next chapter then. What this allows you to do, though, the powerful part about this is that now you can better understand how the digital filter has to be designed to have a particular impact on some analog signal that's passing through an A to D, going to the digital filter and coming back out through a D to A. And we don't have a real-time DSP system that you can play with. I've been studying this problem, how to get something into your hands in this class that you could play with, and I've been waiting to evaluate something from National Instruments all semester that was promised to me at my workshop in January. It's just about ready to finally show up. I thought it would have been here in February, but that's what phones are for, right? Or in emails, when people ignore your emails, finally you go a different route. And then I was on a phone call today, as a matter of fact, with a guy that said, "Have you got it yet?" And I said, "I got an order invoice saying it's been placed, but I'm disappointed because it says I won't see it till the end of this month, and I'm virtually going to have no chance to use it in this class for a demo." And he said, "I'm going to work on that and try to get it to you much sooner." We'll see. I gave up holding my breath on things like that a long time ago, because I would have been dead a long time ago. Have you ever felt that way when somebody promises something and you start holding your breath, hoping that you're going to have it and do something with it, and then it never comes? Well, seeing is now believing, so seeing the hardware will make me believe. But I'll do a demo of this using some other systems. I have some other cute little DSP systems I can use, and another system that I've been trying to build with a microcontroller and what I'm calling a poor man's real-time DSP. I just haven't had enough time to spend on that one, but I've got some other systems too. Last little thing in this chapter is just reflecting back on the moving average filter, which basically has two parts to it. It had an amplitude response part, this purely real function, and then times that e to the j function. And that e to the j function corresponds to a filter that really just delays the signal by n0 samples, because that's what the frequency response would be. If the impulse response is just this n0 sample delay, find the frequency response of that and see that's this purely linear phase, as we call it. The phase just slopes downhill with slope of n0. Remember the first part of the lab last week, you put in a signal which you delayed by 4 samples, right? And then you had this moving average filter, and how many taps did that moving average filter have? Anybody remember? Well, the second part did. In the very beginning, though, how many taps? I was thinking it was 9. It's 9, right? It was 9 total taps. So guess what 9 minus 1 over 2 is? It's 4. And that's That's because this is the N naught value for this particular type of filter. So that's why it introduces a mean delay of L minus 1 over 2. So that's this bullet right down here. No accident, actually. Now, the delay is there, but the signal also gets attenuated by the amplitude response, the D sub L part. So the signal picked up an additional amplitude scale factor, but the waveform was shifted by that 4 samples exactly. Depending upon what type of project I'm going to give you the final project, one of the final projects has got a time-varying delay in it, which sounds kind of bizarre. You believe that you can make a time-varying delay? I mean, it's definitely not going to be a time-invariant system if the delay changes over time, but have any of you heard of the audio effect called flanging? It's an ancient, dates back to the 60s and 70s, when everything was done analog. Flanging referred to putting your hand on the tape recorder reels and actually slowing it down and letting it speed up while you were re-recording the mix from a studio session or something. So it's still called that because it dates back to mechanical means, but a digital or DSP version of that is something that I have in one of the projects, and it uses a continuously varying time delay. So if you can send a signal through a time delay that changes with time, then you can create a Doppler effect on the signal, because basically you can stretch time out and then press it back together again. And we know what Doppler sounds like when we hear a siren or a train horn. As it comes at us, it gets pressed, so it goes faster, and then when it goes by, it stretches out and it goes slower. So with this gadget in software, you can create some interesting special effects, all under software control. Whereas a fixed filter like this one is just a fixed delay. I'll explain more of that if that's the project that I decide to go with. Again, though, that's a DSP thing, so, but we've talked about that before too. We've talked about how, pretty sure we talked about in this class how when you get into the professional recording business and if you're a soloist, you don't necessarily have to have perfect pitch. And I always think of the TV show American Idol. Maybe they have to have perfect pitch to get noticed, but once you start working in the studio, you can doctor your voice up and do pitch shifting and tuning and things like that electronically. And we can blame that on ourselves. We provided that to the entertainment industry. Is that good or bad? That's not for debate in this class, though. Okay, this is the sheet that you should have in front of you. This is the type of thing that the quiz could have contained in it, something along these lines, just like the example we were just looking at. So in this case, we've got a 10 kilohertz C to D. We have a simple low-pass filter, and then we have a 10 kilohertz D to A. Actually, let me just comment on something. With these systems in general, and the thinking of the way MATLAB works, remember when I was playing the bat sounds back, remember that day where we listened to the bat echolocation sounds? You can record at one speed and you can play back at a different speed. You can't do it in real time because you'd have a buffering problem, but if you're willing to record and then play back later, you can, change the speeds. So you could actually totally warp the frequency axis by just playing back at a different speed. And MATLAB's sound function lets you do that very, very easily. I don't know if any of you played with that when you were doing the labs earlier. Did you try changing the sampling rate and just... Okay, Aaron, you did? Okay. Did anybody else do it, though? That's another thing that you guys don't know about. I grew up with a record player, so With records, you could slow them down or speed them up. Or you could put your hand on the turntable and make it play faster, or put your hand on the side and slow it down. The analogy in DSP is changing the sampling rate, just making it crank the samples out slower or faster. That would warp the entire spectrum, so we won't get into that here, but we could analyze that without a problem. So we've got a sinusoid coming into this system at 500 hertz and at 2,000 hertz. So from an aliasing standpoint, we're good, right? So now let's get some answers. So I guess what I'm shooting for, I would like to maybe break the class into 2 sections right now for this analysis. Say, I've got to think left to right. We'll break it down the middle, so we have a line going down the middle. We have most everybody is on this side, and very few people on the other side. So the class half that's on your right will take this signal right here and just pump it through and find out what its contribution is at the output. And everybody that's on the left-hand side, just work on pumping that one through. So what I'm interested in, I'll call it Y 2K of T equals and Y 500 of T equals. What do they look like when they come out of the system? This is going to require a calculator, so it's not something you can do in your head that readily. So I'll just let you work on this for a little while. Feel free to move and talk to somebody else if you want to, or if you just want to work in pieces, or just the easiest thing to do is be entirely parallel based, right? Everybody does their own work and you're just a massive parallel processor with redundancy. So in getting ready for these answers that are going to come flying out here really soon, I've got the blanks ready to get filled in right now. So if anybody's got any of the blanks ready, to give me an answer right now, like the omega hats. Those you should already have. I was going to bring my calculator down, but I didn't do that, so. How about omega hat 500? Does somebody have that from the fat side of the room? Fat is in the largest number of people. Yeah.
Consistent?
Well, here, if you'd done it the other way around, I meant it to be on your right.
I did 500. Okay, so 0.1 pi.
Okay, so it's the other way around, that's fine. So you have 0.1 pi. Okay, so what's the omega hat 2000?
I just got 1.256 radians.
Okay, how about just in terms of pi, just make it be more friendly looking. Actually, the 0.1 pi, well, okay, what did you say for the 2000? It's 0.2, isn't it?
It should be 0.4 because 2000.
Oh, that's right, 2 times it. Never mind. Yeah. And 5 over 100 times 2 is 10 over 100, which is 0.1. Okay. So now we have the 0.1 pi. So now we need to have that in polar form. Okay, any answers? Yeah, for the polar form.
Just got 1.17.
This is for the 0.1 pi, right?
No.
Well, for the 0.4 pi?
Yeah.
Okay.
1.17 times e to the 0.925j.
Is it plus or is it minus?
That's plus.
Okay, you're saying what?
Yeah, it's plus.
Anybody else concur? So 1 point, what did you say?
1.17 times e to the 0.9425.
1.17 times e to the, I was thinking you're giving me the angle.
0.9425.
Okay, I'll just go 0.94. Okay, what about for the other one? Anybody have that one? For the 0.1 pi? I've lost track of who's doing what because it seems like it's mixed up, but.
I've got the answer now.
Okay, well, put it out there and we'll see.
Got 0.3129 e to the j 0.45 pi. Or
At a lower frequency, we have a lower amplitude. This is a low-pass filter, so I'm suspicious. This filter has the shape kind of like this. It's going to roll down. That's right.
That's why I looked at that.
Anybody else work that one out? But we know the 1.17 is correct? Or at 0.4 pi? Okay.
The 0.1 pi is just 0.31 times e to the 1.4 j, which is 0.45 pi.
Okay, the amplitude is what again?
0.31. Yeah, it still doesn't make sense.
That doesn't make sense.
That's what everyone giving us here, though, so obviously it's doing something wrong.
I can start up MATLAB or Mathematica. Actually, we know something as a sanity check on this filter. What is going to be the DC gain of the filter? We said omega equal to 0. We get 1. That is a high-pass filter. Never mind, I was thinking it had a plus sign in there. So that is correct. You guys are correct. I was wrong. I was thinking it's a high-pass filter, so it's doing something like, it's actually doing something like this. So at omega equals pi, we have 2, and then we have 0 at DC. Okay, so going back to the numbers you had now, it's 0.3 e to the
1.4 j.
Okay. So if those numbers are true, then what do we have down below here? What do we have for the 2K then? What do we have to do to get the amplitude out in front of that cosine at 2 kilohertz? The filter is giving us a gain, a magnitude of 1.17, but that gets applied to, what's the input amplitude?
Yeah. So it'd be a two-tap filter, right?
Mm-hmm.
Right. So divide by 2. So I got for 500 hertz.
Well, the taps doesn't matter in this case. The filter's frequency response is just given by this thing right here, and that's that. So we know that the gain of that filter at the 2 kilohertz is 1.17 e to the j 0.94. But what matters here is that's the gain that gets applied to this upper signal up here.
So we still need that for L so we can plug it into the equation.
There's no L here. L was a different type in the moving average filter. This filter is just defined exactly as this. There's no L in there. That's for a different type of filter. That's the beauty of our model here, is we can have any type of h of e to the j omega hat, namely any type of digital filter. That was for the moving average filter. And that's why you've been solving the math for, get this thing to shift modes. You've been evaluating h of e to the j omega hat at the 0.1 pi and the 0.4 pi by plugging in, to the filter's frequency response function to get what its magnitude and gain is at that frequency. So you've told me 1.17 is the gain applied to the 2 kilohertz signal, because that becomes the 0.4 pi in omega hat digital frequency domain. And what is the amplitude of the cosine wave that comes in at 2 kilohertz? It's 20, right? So that signal flies in at 20, and then it hits the filter, and what does the filter do to it? Multiplies the 20 by the magnitude response of the filter, which is the 1.17. So 20 times 1.17 is what? Just to have the number to put in here. And then the phase is going to be, according to what you've told me, it's going to be a plus. What is the angle now? The signal comes in with a phase of 0 because it came in as a cosine angle 0, and then the filter imparts some additional phase shift to the signal, right? And what is that phase shift? It's exactly the phase shift of the filter at that frequency. And what is that phase shift? You gave it to me, Kevin.
It's
Yeah, exactly.
Are you guys calculating that? Are you just sticking it into your TI-89?
Yeah.
Okay. Because what I did was I took that h of e to the j omega hat equals 1 minus e to the negative j omega hat, and I factored it down into the trig form, where you pull out an e to the negative 0.5 j omega hat times 2 sine 0.5 omega hat, and I'm getting the same amplitude values, but for my phase value, I should just be getting values that are e to the negative 0.5 j times omega hat, and so those phase values seem different than what you would be getting if you went through that method. So I'm not sure if those phase values are.
Okay, well, I'm starting up Mathematica.
I could be wrong. Maybe I'm just looking at it wrong.
I'm going to put up the solutions to this later. See which has less strain on my computer, MATLAB or Mathematica. Okay, that's good to go. Okay, so what we were trying to do is we were trying to calculate ABS of 1 minus J of 0.4 pi. And I want it to give me a numerical value. Okay, there's that guy. And arg is angle. Okay, that's what you guys gave me, right? And then the other one was 0.1 pi, right? That's what you gave me, I think. I mean, within decimal points, of course. And then we wanted arg. That's what you gave me, to within decimal places. Okay, so we're good there. Okay. So now we go on to the 500 hertz, and you should be able to get that one now following the example. So the 500 hertz signal comes in as 7 cosine. It has no additional phase shift on it as it comes into the system. So what comes out now?
3.1.
And then what's the angle? Why is it 2.17? Well, yeah, what did you do, Kevin? You took the 0.31 and you multiplied it by what?
7 times 0.31, 2.1.
Now what about the angle? The angle comes in at 0 because the cosine has no additional phase shift on it, and it picks up the phase shift of the system. And what phase shift does the system apply at that frequency? At 1.414, which I guess is not, according to my calculation, wasn't 1.414, but it was at least 1.41. Yeah, something. And that's it. Now suppose I tweak the problem slightly and suppose there was a phase over here. Suppose there was a pi over 3 thrown in here on that particular cosine term, then what would happen down here? That just rides on through, right? What are some of the hang-ups that you're seeing, or confusion factors?
Doing it without a GIA guide.
Okay. We can take that up after class in terms of, that's a mechanics thing. I guess I could, for this simple filter though, what you did, Jeff, is on the right track, but another way of getting at it directly would be to just go, write it out in straight Euler's form. It would be 1 minus cosine of 0.4 pi, let's say. And then you would have, plus or minus a minus, so it would be plus j sine.
I was trying to go through that method as well.
And then you'd have to take and do the polar conversion. Yeah, so you'd have to take the square root of the sum of the squares to get the magnitude, and then the arctangent, and then watch the quadrant, and so on.
I just don't understand why my method wasn't.
Maybe you missed a sign in the factoring. Actually, it's a sign, so there was a j in there too. Did you perhaps miss a j?
I pulled out that, like the thing you pull out when you're factoring down to the trig form, that's going to be your phase, correct?
Yeah, so you had the 1 minus e to the j omega hat, and I think you said I'll factor out the e to the minus j omega hat over 2.
Yeah.
Then I'll have e to the j omega hat over 2 minus e to the minus j omega hat over 2. And then I have to put a 2 down here, or 2j down there, and a 2j out in front to make that into a sign. So I'm going to end up with a 2j e to the minus j omega hat over 2 times sine of omega hat over 2. And then you got to track that j through when you're doing your polar angle. And, well, it's kind of like to get here to get there from here, there's multiple ways, but there's little tediousness is no matter how you do it. That's why calculators came along for engineers to use. And of course, computers are now what we normally would use, but on exams, calculators is kind of still where we're at. So I've practiced that using my calculator, and that's why I do those screenshots and things off the calculator to try to get you into that mode of being able to think that through.
So the 2J's would cancel.
The 2j would cancel. What do you mean?
Because it's divided by inside. Or would it still, 2J would exist outside?
Yeah, the 2j is out there because I threw the 2j. I threw the right color. This 2j was, I won't shift colors on me. I'm the wrong button, that's why. That 2j was part of, to make the sinusoid, right, from Euler's identity. So this 2j had to be added in to balance that out. What other things are bothering you? I mean, this stuff we've been practicing on all semester, and it can be conquered. If you don't have it conquered now, I'm convinced you can conquer it. But what are some of the other things related to the theory in this area that have bothered anybody?
So my question is, L is only used on an averaging filter.
Yeah, L is one of the parameters of the averaging filter.
So if we have any other type of filter, we can tell it's not averaging, and we can just simply plug it into the given equation.
Yeah, you might have to drive h of e to the j omega, but in this problem, you're given h of e to the j omega. The L was part of the impulse response of the moving average filter. Remember, it's 1 over L times the average of the present and L minus 1 past values. So that's just associated with that particular type of filter.
So you're saying if we were like given delta then, and we derive frequency response from that, then we could plug into the frequency response.
Yeah.
You gave us the actual impulse response.
Yeah, so this is a good little exercise. Last lecture we were talking about how if this was h of e to the j omega hat, how we should be able to go back to the impulse response, right? So if that is h of e to the j omega hat, we also have to know how to do this in general. So what would be the impulse response if that was the h of e to the j omega hat? And then the other thing we were looking at last time was the difference equation. That I guess you could be kind of trying to make lots of analogies saying different domains, different languages, so you have to speak multiple languages here, being able to go from...
In this case, because it's a negative in there, we know it's a sine equation.
Yeah, that's the Euler's business there. But in this case, I don't think I would have done what Jeff did. Not that it's a bad thing in general, it's just that the math is still the math, and I'm more interested in just getting to the answer. And I would see through it without the elegance. The elegance doesn't matter necessarily. It's nice on paper to be able to understand that it's a linear phase filter is what we would get out of this, something that you learn about in the advanced modern DSP class that I teach in the fall. But other than that, you still have to deal with complex numbers. I mean, you still have to deal with a j sitting over here, and the e to the minus j omega hat over 2 is over there.
Yeah, kind of stuff.
You have sines and cosines, though, so you've got, and you have the arctangent, so.
Yeah, I think I'll just do it that way. Because I don't quite see how you can move that j up into the polar.
Okay, well, how does anybody else know what that's all about? I mean, because that's getting back to something we would have done earlier. E to the j corresponds to e to the j pi over 2, right? In polar form, 1 at an angle pi over 2 is the same as j. So then you could just merge those two guys together, and you'd have 2 times e to the combination angle there, pi over 2 minus omega hat over 2. And then that would be your angle for the system, would be the pi over 2 minus omega hat over 2. And then your magnitude would be the 2 times the sine of omega hat over 2. So when you finally get done pushing it around, it's actually not too bad at that point. So actually, if you pushed it far enough, you would avoid having to do much button pushing with your calculator. Well, briefly, since we're basically out of time, I wanted to just introduce, I guess this tells me the quiz won't have any simple Z transform on it on Friday, but that's okay. The Z transform takes us into the third domain, so to speak. We've been working in the time domain. That's where we have the convolution sum and all our sequences. The time domain is the real world. That's where sequences fly around, go in and out of A to D's and D to A's. Frequency domain was useful in the last chapter for getting the frequency response, and that was just an analysis mode we were playing around in. But now we're going to have the Z domain as a third representation, and they're all related to each other. The Z domain is the easiest to work with because it doesn't have any J's floating around with it. So the Z transform of, say, a sequence just looks like a polynomial in terms of a complex variable Z. And so what really makes the Z transform nice is the fact that everything that's ugly is sort of hidden inside of that variable Z. You just think of it as a variable, and you don't think of it as being a complex variable, which is where things can be more ugly. And so, if you don't know the ugliness because it's sort of hidden behind the Z, then you're more relaxed about things. And when you want to go back to the frequency domain later on, you can just replace Z by e to the j omega hat, and then you're back to where we were with the frequency domain.
So you just treat it as a constant.
Yeah, as a constant or as a variable. So when we go to Z transform a sequence, as a simple example here, a delayed delta will just be a Z to the minus n naught, or just looking ahead a little bit. If we had this for our sequence, those 3 deltas in it, we would just get, in the Z domain, we would just get this polynomial right here. And if we want to transform back from the z domain back to the sequence domain, we just say anytime we have a power of z, we just look at its power, and if it's z to the 0, which is 1, then it's just a straight delta. If it's like a -2, it's just a delta -2, and so on. Experience has shown you guys take to this very, very quickly. This becomes like taking medicine that has lots of sugar in it. It just goes right down, no problem. If that's a good analogy, I don't know. For me, with my metabolism and my conditions, I can't have the sugar anymore. But if you're not diabetic, I guess then the sugar is maybe good for you. I don't know. Or makes you feel good. So we'll get into that, and then this is going to lead to some other things. Why do we have these different modeling domains? It's because we're trying to get around problems and have different tools that are better adapted for different types of scenarios. And we don't like doing things the hard way if there's an easier way, and that's, we're always in search of a tool that helps us view and understand things more readily. They all have a place, though, and that's what I'm going to have to do is, and hopefully I can convince you this fairly readily. What can we do with it that's useful? So I'm signing off.